So those of you who are on the CERIAS email list, you have gotten multiple announcements to us of Purdue and CERIAS's involvement in the DAHCS program with the Department of Energy. William Zortman is with Sandia National Labs, is a systems security engineer, and is the campaign manager for DAHCS.
All right. Thank you so much, Joel. Appreciate it. Okay, so yeah, this is all about DAHCS. I work at Sandia National Labs, and at Sandia National Labs, we are responsible for the non-nuclear design engineering for nuclear weapons. So a pretty important job. We have other, so that's a high example of a high consequence system. We have other high consequence systems that we work on. We have a active hypersonics program, worked with Purdue on that as well in kind of a different area, satellites, and also power systems. Satellites, we actually do some work on. Power systems, we're more kind of in an advisory role, providing capabilities and technologies to those systems. All of these systems are high consequence, meaning if something goes wrong with them, you have a massive loss of life, you have a change in maybe the strategic position of the United States or some other major consequence. The nice thing about these types of systems is they are constrained. It's not like we're starting this program working on enterprise systems, for example, which are very unconstrained systems, easy to update and connect to lots of places. These systems are designed in particular, especially nuclear weapons. The philosophy when people are designing nuclear weapons is, hey, we don't need to upgrade this thing. We don't need to make it extensible. We don't need a bunch of features like you have in other systems. You have a very limited set of things you want to do, a very specific thing you want to do, and you don't want to do anything else. So for us, this is a very good place to start because it's a constrained system. In less constrained systems, it gets very expensive to do red teaming and assessments and understanding vulnerabilities. So I can tell you, in my experience, I most recently was doing red teaming, a lot of assessments. So assessments meaning working with design teams and developing systems. And I had one where we spent $100 million and spent 10 years on one component, doing an assessment on one component. That did not include the design changes that the engineers had to go and do. This was not a Sandia system, different system. The design changes the engineers had to go and do to fix that component. Probably a half billion dollar component when you're done talking about it. That is an example of an unconstrained system. Some of the constraints in that system were actually helpful to us. So we knew that we wanted to prevent one thing from, there was one thing the designers were really worried about, the program managers were really worried about. They wanted to prevent one thing. So we knew what our consequence of compromise was. We knew that if an adversary was going after a vulnerability and it led to that compromise, that was something that we had to pay attention to. But other vulnerabilities in the system, we didn't have to pay attention to. So that constrained our system, let us spend less money. What cost so much in doing the assessment on that component, I'm sorry, it was a component, not a system. What cost so much was the threat model. It was the threat model of one. It was the adversary knows everything about your system and has full access to your system and has access to every capability that we can possibly think of at Sandia National Laboratories. And we can think of a lot of capabilities. There's 16,000 people there. A lot of them work in cybersecurity, hardware security, and other areas like that. But then we got all these other scientists and engineers in other areas, so we can bring multidisciplinary attacks against systems. There's a lot. When you have a threat model that is unconstrained, you're going to end up spending a lot of money. At no point in that, doing that assessment, did anybody say, hey, what if we said the adversary maybe couldn't do a few things? How much would that change the cost structure of, how much would that change the expense of this system? How much would it change the expense on the assessment, and how much would it change the expense of the design that we're influencing through this assessment? And no one asked that question. Not sure it was relevant to that component, but when you look at systems in general and you look at doing assessments and figuring out where vulnerabilities are, you can't really ask that question. You can ask it, but you can't really get an answer to that question because changing the threat model doesn't result in someone being able to at least get an idea of how much money we're going to save. So threat model is one component of doing assessments and understanding the vulnerabilities of the system. Of course, there are others. In my experience, so that is a limitation on the way we do red teaming, assessments, understanding the vulnerabilities in our system. And it's a limitation on the way we do that because we don't have digital assurance integrated into the discipline of systems engineering. That has not happened. I have a really good friend of mine from years past. We used to do assessments together, who's trying to integrate different artifacts from cybersecurity into a systems engineering model, and he can do it. He's successful at doing it, but the language is completely different. Every time he looks at a new system, he has to go modify the MBSE model in order to make the threats for that system relevant to the engineering in that system. So if you're a systems engineer, you're not working with a model that can tell you something about your risks. You're just working with a model. And then you have some cybersecurity engineer out there who maybe you have access to and you go talk to, and that results in some of these quotes here. I'm not sure you can see them from back there. I can barely see them from up here. But basically what the quotes all say is, well, we have a great relationship with these cyber people. They're really wonderful. As long as you get them involved early on in your system, things work out great. Well, that doesn't sound like a relationship where we actually have systems engineers who know something about cybersecurity and who have tools that can integrate it. They can do that with reliability engineering. They can do that with safety engineering. We can't do that with digital assurance. And that's what we're trying to fix. We're trying to take some of those metrics like threats and other things, integrate them into the systems engineering process so that people can make trade-offs. They can come up with a risk profile for a set of vulnerabilities or a vulnerability or overall for the system and decide which ones to prioritize, and also decide if they want to prioritize addressing those vulnerabilities against making the thing go faster, saving some money and putting it somewhere else, something like that. Okay, so this is what we're trying to do with DAHCS. This is, so there's 5 things across the top. I can summarize that for you. Rigorous is definitely something we want to do. We want to be able to evaluate what level of assurance we have. Rapid and cost-effective that's efficiency. So we want to be rigorous, we want to be efficient, and we want to be generalizable. It says across systems life cycles, we have to be generalizable because it goes back to that current project where people are trying to integrate vulnerabilities into systems engineering, and the ontologies are different. There's no general ontology to combine those things. So generalizable, that's what that means, is we have to be able to apply this lots of places. And of course, that'll be across the systems life cycle. And the vision is to be able to make trade-offs against digital assurance, not have threat models out there that are, it's basically the boogeyman threat model. And you go to these people, and I've done this many times, and you say, here are your vulnerabilities. Sometimes they say, great, let me try to fix some of those. A lot of times they say, you're just the cyber guy who brings me a bill every time I'm done building my system and I don't want to change it, and they just move along and don't do anything, so that we can manage and accept risk. Okay, so if you're going to do that, let's talk about rigorous. If you are going to do that, then you need some sort of measure. We do measure the security of systems. We can measure the security of AES against a brute force attack. Maybe not against all attacks. We don't know. There may be some attacks out there that are successful at AES. No one's ever published one. But we can measure the effectiveness of AES to protect itself against a brute force attack in years. And we can also measure it in the energy expended. You got to spend a lot of energy to do all those computations to run AES over and over to find a key. Bitcoin is similar guarantees against certain classes of attacks. But with systems, it's different. We are dealing with an asymmetric threat. And that's the real problem. You put all this money into these systems, and then someone comes and says, you got to put more money into the system to protect against an asymmetric threat, and more asymmetric threats may surface. And so it becomes a never-ending struggle to try to prevent all of these different threats. And so I assert that it's not about spending money to secure these systems. And I think you probably all agree with me. It's really about being thoughtful in how we design systems. That's the most important thing. Not only that, but some of the tools that we've come up with, people are actually looking at these saying, hey, this might actually make our engineering more efficient. We might actually be able to do things more quickly. Okay, let's talk about measures. So levels of assurance. And when we talk about measures and being able to compare things, we always put a chart, with an x-axis and a y-axis. That's why there's an x-axis and a y-axis here. But levels of assurance are measured how? I'm not really sure. That's why there isn't anything on this axis. This is one of the things we're trying to figure out. If you go talk to JFAC, they're here in Indiana. They're very close. Well, a lot of them are here in Indiana. They're also in Washington, D.C. But if you go to Crane, in Indiana, which is the landlocked naval base that you have here. They have levels of assurance. It's actually steps as you go up. I can't remember exactly how many. And they talk about levels of assurance for firmware and software and hardware and different things, ASICs. So there are measures that exist. There are standards. You can follow all the standards, and then you have a measure of assurance against some standard that folks have put out. But this is difficult. Is it measurable quantitatively? I think probably in some cases you might be able to find places where it's quantitatively measured. AES is an example. But a lot of times we're going to be talking about qualitative measures. But we don't even have that, that sorted out. And it's to the extent where we don't have the tools to be able to decide what we want to do in a system. What's the priority that we want to fix in a system? And then we have stuff that's out of reach for us today. So this is kind of the highest effort or complexity that we can assure today. One of the things we'd like to do on DAHCS is figure out how we can reduce the effort that we put into assuring systems and still maintain the same level of assurance. Again, you need to measure if you want to do that, or maybe we can increase the level of assurance without spending any money or spending less money. That's the thought. Putting thoughtfulness into how you do a design is where that comes into play. And then finally, how do we do out of reach systems? So there's some systems that are so complex. I mentioned enterprise systems at the beginning, but think about really old systems. We've got some old systems in the defense complex. Think about some of those old systems that are out there. There's systems that are out there with processors that were designed in the 1980s on a process node that some multiple number of microns. Those systems, the manuals and things don't exist. How do you understand what the system even does so that you can figure out what your vulnerabilities are? Well, you have to. You could do a full RE of the system. Some people actually do that, but it's very expensive. So a lot of those systems are out of reach. Okay, so here's an example of, and this is just an example of how we're thinking about this problem. How do we put together all the pieces in order to do this? I'll start with good to start with the end in mind. I read a book about that once. We want to make systems that are assured by design and assured by inspection. Sometimes you assure by design. Formal methods is a good example of that. Sometimes by inspection. Full chip RE is one way you could do it. That's kind of expensive. In my experience, I've seen assured by design. Software people are a little better at that than the hardware people. The hardware people tend to go to inspection. Multiple reasons for that. But then if you look over here at the left, I talked about threat models earlier. We have a lot of them. MITRE ATT&CK is one. There's a bunch of them out there. They're all in natural language. I would say they're not integrated very well, most of them. And because they're in natural language, if I want to do assured by design and I have a formal model, how do I combine those things? And how do I combine those things in an efficient way so I'm not manually combining these things like we see people doing today, put them both into a formal model, and then I can do that. You can see some of the projects that we funded. Some of these are converting natural language into formal language. So there's some AI tools that we're looking at to do that. Others are theorems of sound composition, taking something that would work on a single state machine and looking at it across multiple state machines, and still being able to prove that our requirements are being met in those cases. I mentioned ontologies. This is a really hard project. This is about creating an ontology to reason about to reason about the security of a system, to reason about the digital assurance of a system. It is taking the language, for example, of hardware security, the language of cybersecurity, the language of supply chain security, combining that with threat model language, for example, and making all the words make sense for system level so that we can reason at the system level. That's really important if you want to incorporate this into model-based systems engineering. It's not just model-based systems engineering. We use a lot of design tools, right? EDA tools in the microelectronics industry. all of these things that we're talking about doing on DAHCS depend on ideas like this in order to combine language, but also to be able to figure out how to take threats and put them into those design tools so that people can make trade-offs. We, if you look at the EDA tools, they're really great, right? Because you can look at a thermal profile of a chip and say, boy, that thing's getting too hot. I'm going to turn down the performance a little bit. I'm going to change the layout, do whatever I'm going to do to make all these trade-offs, but we don't do that for digital assurance. And so that's an important part as we look kind of out to the future of DAHCS. An important part is being able to integrate into those commercial tools and potentially IP as well in how we design systems to make them more analyzable. Okay, lots of partners. And some of these are fellow travelers. They're not even really partners, but lots of people are looking at these problems. You can see JFAC there. They've been a really great partner. Folks, a lot of them, they're in Crane, Indiana, as I mentioned earlier. I will wrap up very quickly. So this is, if we want to collaborate with you, and we can send money to universities. So Purdue is one of the universities, strategic partner with Sandia, very important partner for us. This is the time to do it kind of until May. Starting probably in December is the time to contact PIs, but you can contact me. I'm happy to hold hands and get people together. That's how collaborations happen. It's not going to a website or something. That window that starts in December, so the very beginning in December, there's a MyCop where you can get online and we actually do the pairing with you it's a Teams meeting. But throughout the year, you can be a part of this. And the way to join that is DAHCS, DAHCS, -MyCop, MICOP at sandia.gov. And you can just send an email to that. They'll get you on the distribution list. And then there's hundreds of people from across the country that talk about DAHCS. And they're just bringing their own research, their own ideas, whether it's game theory or something else, and talking about it in that forum. People get to know each other, and that's how those collaborations get kicked off. And that's me, and thank you very much. If you have any questions.
Any questions?
Mine may hopefully be quick. In your simplified kind of chart visualization, it seemed like assurances versus resources was the main comparison. How have you been factoring in those kind of core missions and needs of these high consequence systems in that evaluation?
Well, that's what we're trying to figure out is how do we incorporate the other needs of a system against digital assurance needs. And that level of effort, I don't think I identified that specifically. That could be money, that could be time, it could be the length of the length of the program. So a number of things that would impact how much effort you're putting into the assurance, and we want to be able to trade against those things. Okay. Yes. So yeah, MBSE, sorry if you don't know the acronym, stands for Model-Based Systems Engineering. So those are engineering tools that systems engineers use to understand systems at a high level of abstraction, at multiple levels of abstraction actually. And so they have requirements that flow into those tools. These are computer tools. And then they go about doing their design. They take information from lower levels into the system. For example, a processor, they're not going to have all the data about how that processor works, but they will have information about what job that processor is doing, how long it takes, those types of things.
William, thank you very much.
Thank you.